we define angular velocity to be the rate at which angular position changes. That is, we use omega for angular velocity, and that's going to be our change in angular position divided by our change in clock time, and that should be omega average. I can't write average easily from this angle. I'll just put a bar over my omega. As a reference example, if we move from position theta equals 2 radians to theta equals 6 radians in 8 seconds, we have a delta theta from 2 to 6 radians of 4 radians, and we divide that by the 8-second time interval, and we get 0.5 radians per second. And our units, of course, are radians per second. Angular acceleration is the rate at which angular velocity changes. Average angular acceleration is change in angular velocity over time interval. And of course, angular acceleration is the limit of that quantity as delta t goes to 0, the derivative of angular position. Fundamental example, if we accelerate from 12 to 20 radians per second in 4 seconds, then we have a change in angular velocity of 8 radians per second, spread out over 4 seconds. Then on the average, we have 2 radian per second squared acceleration. And the units, of course, are radians per second squared. What about angular kinetic energy? Well, not being real consistent with the way I defined kinetic energy before, say that angular kinetic energy is total energy due to rotational motion. It's really, we could define it as before as the work required to accelerate an object from rest to an angular velocity, a given angular velocity omega. The rotational kinetic energy is then is not defined, but we find that the angular rotational kinetic energy is 1/2 I omega squared. And we can easily prove that. That's not a definition, that's the work done to accelerate this thing. Or if we prefer, that's the sum total of the kinetic energies of all the particles in the system. Okay, if we have a disk, for example, with, as a reference example, disk with a moment of inertia of 3 kg/m squared rotating at 5 radians per second, then its kinetic energy of rotation is easily found to be 37.5 kg/m squared radians squared per second squared. Now, this meter squared is a meter squared of arc, because when this thing's rotating, the kilogram-meter squared, remember, the meter squared here comes from a meter of distance from the axis of rotation. When we sum up all the mr squareds, that's what the meter is. So that's actually a meter of arc when the thing starts rotating. And when we multiply a meter of arc by a radian, we get simply a meter. Because, of course, a radian is the angle such that a meter of arc corresponds to 1 radian angle. So the radian squared can simply go away. If you're curious about why radians go away sometimes and why not, this is one way of explaining it. So we have kilogram-meter squared per second squared, or joules, when we do this. And of course the units are exactly what we used here, kilogram-meter squared per second squared, or joules. Just a quick digression to the most basic relationships between angular and linear quantities. Displacement is analogous to angular displacement, or angular position is analogous to position. Angular velocity to velocity, angular acceleration to acceleration. And we can take the equations of kinematics in terms of time intervals, initial and final velocities, and displacements and accelerations, and translate them directly. The reasoning that we get, the reasoning that we use for these quantities is identical to the reasoning that we would use for these quantities. And we can see that, and I hope we have seen that in this course, so that we can simply substitute thetas for s's, omegas for v's, and alphas for a's in the equations of kinematics, of uniformly accelerated motion. F equals ma translates into torque equals moment of inertia times angular acceleration. Remember that moment of inertia is thought of as the resistance to angular acceleration in the face of a torque, just as mass resists acceleration due to a force. Kinetic energy, as we just saw, 1/2 mv squared translates to 1/2 I omega squared. Momentum mv translates to angular momentum I omega. Now, there's an important distinction here. This kinetic energy is the same as this, measured in the same units, and it measures the same things. It's energy. But angular momentum is not the same as momentum, as we can see if we look at what the units of angular momentum are as opposed to the units of momentum. We get kilogram meters squared per second here, kilogram meters per second here. They're completely different quantities, and they do not translate. We can't convert angular momentum into linear momentum. And conservation of angular momentum is an important law, as we've seen. And then mass, of course, being analogous to moment of inertia, which is what we get when we sum up our mr squared contributions.